two events are, ready? Disjoint events. So here's the first funny word for today. These two events are called disjoint events. What are disjoint events? This event here, selecting a 5 from the deck, and this event here, selecting a 9 from the deck, are called disjoint events. Well, what's the textbook definition? Disjoint events have no outcomes in common. Yep. They share no outcomes. They have no outcomes in common.
So is this the same thing as like in discrete math or and you did?
Yeah, exactly.
Okay.
But that's the textbook definition. You go, what are disjoint events? They're two events that have no outcomes in common. Well, everyone, that still sounds confusing, doesn't it? So can we break that down and make it very simple? Ready? I'm just going to pull out one card out of the deck. I'm not going to show it to you. Is it possible for this one card to be a 5 and a 9 at the same time?
No.
Disjoint events. So would you remember that? If you're ever confused about what are disjoint events, I want you to go back to this example and say to yourself, and hold up, and think of me holding up this one card going, this card here cannot be a 5 and a 9 at the same time. That means they're disjoint events. They have no outcomes in common, right? But see, I think you get this. Like, could this be a 9 and like a heart at the same time? Think about that. Is that possible? Oh yeah, so those are not disjoint events. Let me say it again. That's why it's good to learn from cards. You go, can this be a 9 and like a heart at the same time? You're like, oh, that could happen. So those two events would not be disjoint. But these are called disjoint events. And when you have disjoint events, you just add it. All right?
Like mutually exclusive, right?
Yeah, and that's another word for this. I'm going to write it up right now. Another word, it means the same thing as disjoint events. Are mutually exclusive events. So both of these mean the same thing. These two events are mutually exclusive. You may have heard that phrase before. So disjoint events are mutually exclusive events, right? The events selecting a 5 and a 9 from the deck are disjoint events. So in terms of probability and the probability rule, if you have disjoint events and you got to find the probability of this occurring or this occurring, we're just going to do what? We're going to add them, right? So now you're like, yeah, can you give us the rule though if they're not disjoint? So here we go. I'm going to write it out as events A and B, and here we go, 5.2, the probability of A or B occurring. This formula will account for everything, so we'll call this the general addition rule. Does that sound good? This will be the general addition rule. This works in all probability for all events. It'll be the probability of A plus the probability of B minus, this is going to be funny, A and B. The probability of A and B. But now if you hear this phrase or in probability, you're thinking addition, right? Mm-hmm. But now in this part at the end, we're going to have to subtract that out if the events are not disjoint. Okay? But, hey, we can play this safe. We can do this every time. That way you never miss a probability problem. How about we do this every time? So I'm going to do it right now. In this problem, I had probability 5 plus the probability of 9. We got the answer right, but I'm going to write this. Minus the probability that it's a 5 and a 9 at the same time, right? I want you to subtract that out. Probably a 5 and a 9 at the same time. Okay. That'd be 4 out of 52 plus 4 out of 52 minus, how many ways can it happen?
0.
0 out of 52. There are 0 ways it could be a 5 and a 9 at the same time. So that's what they mean by here. But we'll include this if the two events are not disjoint, right? This will work every time. So our answer is still 8 out of what? 52. So let me give you another problem. And we'll compare it to this problem. Sound good? So great job with that. You're like, that problem wasn't too bad. All right, now try this one. What's the probability? You select a 6 or a diamond from the deck. A 6 or a diamond. Well, I think I'm gonna have to race this up here. Can a card have a 6 on it and a diamond at the same time? All right, then we're definitely, when we're doing this on a test, we're gonna have to go through all 3 of these. We can't skip over this. We need this, right? Because this will not equal 0. By the way, you want to make up your own theorem? If your 2 events are disjoint, guess what this has to be every time?
0.
0. If your 2 events are disjoint, well, these are not disjoint events. So when I'm erasing this, because these 2 events are not disjoint. So let me start out. I'm going to have to do probability of the 6 plus the probability of it being a diamond. Here, we can just draw a diamond. Minus the probability it's a 6 and a diamond same time, right? 6 and diamond at the same time when I pull out that one card. All right. How many 6s in the deck? 6 of them?
Yeah.
Good. 4. There's 4 of them. There's 4 6s, there's 4 9s, there's 4 jacks, there's 4 kings, etc. Except for diamonds. Hold up. Diamonds! That's all these, right? That's all these. That's all these. How many diamonds in the deck?
13.
13. And now we subtract some. How many cards in that deck have a 6 on it and a diamond at the same time? There's not many. Just one. Don't agree? There's just one. Can I find it? Well, I found the 6 of clubs. It's in here somewhere. I'll do a quick search. There's a 6 of hearts. I'm looking for it. Come on. There's a 6 of diamonds. Come on up. 6 of spades. It's probably sitting in my vehicle or something, right? I probably only have like 51 cards here. All right. And there it is. There's that one card, 6 of diamonds. I'm going to subtract it. There's only one of them. So the answer to this math problem is not 17 out of 52. It's what?
16 out of
16. 4 plus 13 minus 1, 16 out of 52. Or, want to reduce that? 4 13ths. Or, these are equals. Or
31%.
31%. 31%. So 6 or diamond at the same time. Hey, my chances of doing this are still kind of low. Do you agree? Yeah. It's still like, I don't know. 31% chance is not good. Is this a 6 or a diamond?
No.
I lost again. I didn't have a good chance of doing it though, did I? I didn't even shuffle these, but if they're totally random, you only have a 31% chance. Hey, super job with that. Hey, one more of these because I know they're kind of tough. You're like, not tough, we got it. King or a face card? And see, when you read the question, it sounds actually a little confusing.
Isn't king a face card too?
Yeah, because the king is a face. They're like, what's the probability to select the king or a face card? And you're like, sounds like a confusing question, but we're going to go through the probability rule. We're going to get the exact answer. Right? We'll go through this rule. So I'll do what's the probability of the king. I'll add to the probability that's a face card. But I have to subtract out the probability it's a king and a face at the same time. Okay? Hey, how many kings in the deck?
4.
4? Do you remember how many face cards there were?
12.
Yeah, there's 12 because There you got the jacks and the queens and the kings. There's 4 of each of these, so I'm gonna have to do 12. But okay, this is interesting. How many cards in a deck have a face on it and a king on it at the same time? 4 of them. Then we'll get our answer. This question may have sounded a little confusing, but we're going to get the right answer. 4 plus 12 minus 4 is just, oh, it's the same odds as this. It's the probability of just getting a face card, yeah. Just sounded confusing the way it was worded. 12 out of 52, or if you reduce that, that's 3 out of
13.
13.
I didn't get you the last one. 4 out of 12. How did you get? 12 is like 3, 3, 3, 3, 4. Okay.
Yeah, right?
Okay.
3,
3,
3 of these, 3 of these,
and
and 3 of these.
Gotcha. 4. That's all. Okay.
And we're not including those jokers.
Gotcha.
Has everyone got that? You know the joke, we don't have jokers in this deck. So no jokers, just the 52 cards. Hey, great job with that. Well, that's the general addition rule. I mean, you look it up on a Wikipedia page, you would see that. Cool? All right, hey, so now I'm going to introduce the next rule. But this rule actually comes up in 5.3. Oh, see, I'm about to do this multiplication. I think I should do one rule before that. But I think this next rule is common sense to everyone. I'm going to erase all this. Everyone, if someone said there's a 20% chance it's going to rain today, what's the probability it doesn't rain?
80.
80%? Is that agree? That's called the complement rule. That's called the complement rule. So there's actually a rule for that in probability. Let me just say it again. If there's a 20% chance it's going to rain today, then what's the probability it will not rain? 80%. What did they do? I mean, people just shouted it out. They didn't pull out a calculator. They did this in their head. Everything's got to happen to what? 100%, right? Do it again. If the probability it's going to rain today is 40%, there's a 40% chance it's going to rain. What's the chances it will not rain? 60%. And you go, yeah, all right. Everything's got to happen. So we're taking 100%, we're subtracting it. If it was decimals, we'd take 1.0 and subtract it. Okay? So the way that's written in the book, the complement rule, and complement is spelled with an E, not an I. The complement rule, we're saying the probability of not A occurring equals 1 minus the probability of A occurring. That's what we're saying. Right? And there's a little Keno lottery game, and I heard there's a 1% chance. 1% chance I could win that lottery game. Look, there's a 1% chance I win the lottery game. Well, what's the chances I'm going to lose
99.
when I play it? See how fast you are? You're like, oh, you would say the probability I do not win would be 1.0 minus this 0.01 of winning. It would be left with this, oh, really, really strong chance, 99% chance that I'm not going to win. Does that make sense? It's called the complement rule. I noticed I was watching, and this is fine. A lot of you are like, I don't even have to copy that down. Because you understand that logic, right? You understand that totally, this logic of the complement rule. But you're going to notice how powerful this is in statistics and probability. This idea of the complement rule, it's very helpful. It's very helpful for us. When the probability question gets really, really challenging and difficult, we may have to go to the complement rule. All right, so that'll come up. 5.3, we're going to do the multiplication rule. So, hey, I'll put it in quotations again. Or. I said, if you hear the word or in probability, just think simply you're really doing what? Aren't you adding probabilities? Well, when you hear this word and, basically, would you think
If multiply.
multiplication? Now, these are not rules. I just want you to think this way. Because you read word problem, you go, what's the probability that he hits the first basket and the second basket? Right? Mellor Trimble's at the foul line. He gets 2 shots, right? What's the probability he hits the first or the second? Because if he does that, he can win the game. And then you go, oh wait, to win this game, he's got to hit the first and the second. So what's the probability he hits the first and the second? Those are different probabilities. Those are different chances. And so we've got to make sure. With or we add, with and we multiply. So here comes the multiplication rule. This was called the addition rule. Now we got the probability of A and B occurring. But I want this rule from 5.3 starts out with an if statement. Alright, I am just going to multiply the probability of A times the probability of B. Look at this. Probability of A and B occurring. Probability of A times probability of B, but it has an if statement before it. And it's going to be a new word. What was the goofy word before? Disjoint events? Alright, here comes the second goofy word for the day. If the events A and B are independent events, I'll put a comma, then this is true. So this only holds true as long as A and B are independent events. So we got to talk about what in the world are independent events. I'll let you copy that. That's an important rule. I mean, yeah, you Google the multiplication rule for probability, you get a Wikipedia page that shows up, you're going to see this. But this will not be written solo. You'll have some information about how those two events have to be what's called independent events. So let me define that. And I know a lot of you like to put this in your notes because you're really good at studying your notes, you take great notes. So let me define this in a few words. What do I mean by two events being independent? Two events, A and B, are independent if the occurrence of A does not alter the probability of B occurring. If you don't like the word alter, I can use the word affect. But let me just say that a few times. I'll just say it over and over and over again so you know what do you mean by independent events? Two events are independent events if the occurrence of event A